Alrighty, so we're back. We're going to try and finish this up. Last little chapter we've got before we start doing a review for the exam. Chapter 27 is about inferences about regression. So the AP syllabus, we talk about inferences of the slope of the least squares regression line. Remember back to regression line, that slope of the least squares. We figured this in the calculator, that y hat, the predicted value, equals a plus bx. Our y-intercept plus slope times our explanatory variable. So our slope is an unbiased estimator of the slope beta, okay? And the way you're going to draw beta, if you have to write it, is just like this. We would just say beta. Okay? Normally you just give that the back to the b a little bit of a longer tail. Okay? Now it's possible to calculate the confidence interval for beta and test a hypothesis about the value of beta. And we're going to do that today, and we're going to work through a little bit of example doing this. Let's go ahead and try this out. So in order to do this though, in order to find confidence intervals, in order to run hypothesis testing, we still have the same rules. We're going to have conditions and assumptions. And our assumptions conditions for regression inference is it must be linear data. It has to be straight enough. So we want to look at our scatter plot of our raw data and say, does this look generally straight? In this case, body fat to waist ratio in inches, we'd say that data looks straight. We have our independence assumption. In order to do that, our errors must be independent from one another. We have our randomization. When we do that, the individuals have to be a representative sample from the population. We also want to make sure there's no pattern in the residuals plot. And remember, that's what we want anyways, just to say the linear model is appropriate. We need a nice random residual. Now, equivariance. The variability of y should be about the same for all values of x. And what that means is, does the plot thicken? So if I'm looking at my residuals, are they changing? Okay. Do I see that my residuals are getting larger as we progress? Are they generally getting smaller? Is there some kind of pattern that even though it's random still, does it kind of have a pattern? We don't want that. And what we see, this is almost an idealized solution where all of our values are staying about the same distance away from our line. Our next condition, the normal population assumption. We assume errors around the line at each value of x follow the normal model. What that means is I'm going to make a histogram or normal probability plot of the residuals. I'm going to use, of course, if you've forgotten how to get there, stat calc 8. Make sure you store that regression line because we're going to need that line later for other things. Also, we have to do is to do our residuals. So let's go ahead and try this. First thing is we have some scatter plot, before we even try it, let's go over the scatter plots and regression again. First thing is, how do I make a scatter plot? Well, I'm going to load my explanatory variable into L1. I'm going to load my response into L2, or at least what I think are my explanatory response. I'm going to use that stat calc 8 to run a regression, get me some values. But I'm going to go and do that second stat plot. So let's actually see what that would look like. So up here I have some data. I've already typed it in. In fact, you can see I already have data. I have an explanatory response variable. So if I want to see what this looked like, I'd hit second y equals. Make sure my stat plot is on. It's set for a scatter plot, this one is flashing. And then I want to make sure I'm doing L1 and L2. So I need to change it to L2. And if I run this, I'll quit out there, hit zoom, 9. There's my plot. That line shouldn't be in there. Let's get rid of that line. Okay, we'll try it again. So that's what my plot looks like. That's my scatter plot of my data. So that's how I can see a scatter plot. If I look at this, I see some behavior I kind of like. Let's go into our questions again, though, in order to see exactly what I'm talking about. Okay. So we said how to make a scatter plot. Also, what do we look for in a scatter plot? Well, we're looking to see that it follows a general trend, that there's no clear bends in our scatter plots. If there are, we have to straighten our data. Okay, how do I find correlation? Well, that's why I use that other value. That's where I said I'm going to use that second. I'm going to go into my, get out of there, stat, calculate. We're going to go down to 8. We want to run a linear regression, a plus bx. And if I do this, it says L1, L2. And generally I want to save my regression line, so I'm going to hit vars, yvars, function, y1. And now I have it calculate. So I have my R values, negative 0.525. This is how I find my R, this is how I find my entire model. So remember how we don't find those things, right? What does a correlation mean? Well, remember that correlation. It gives me, am I positive or negative? What's my slope of my regression line? Is it positive or negative? The other thing it tells me is how strong it is. The closer that R value, closer my coefficient of correlation is to -1 or to +1, the stronger it was. So remember, we said R has to be between -1 and +1. And the closer it is, so the closer my absolute value is to 1, the stronger it is. The closer it is to 0, if it's 0, there's no correlation at all. There's nothing, no relationship going on. So I don't want it to be close to 0, I want it to be far from 0, which means closer to 1 or -1. What does R squared mean? That talked about how much of the variability in my response variable was accounted for by my model of my explanatory variable. And we'll get into that again. How do we create the linear model? We're going to use that StatCalc 8. We're going to use that same screen to create a linear model. We'll do that in a moment. How do we know if it's appropriate? We look at our residuals. Our residuals are going to tell us if the linear model was appropriate. How do I create residuals? Well, let's go back and take a look. So if we go in here, as soon as we calculated this, it saved our residuals for us. But we want to see them. So I go back to StatPlot. I go back in here. And instead of doing my x values, instead of doing explanatory to response, I do explanatory to the residuals. So second stat to get to the list, and I scroll down until I find resid. Now remember, if you haven't run a linear regression, there will not be a residuals list. So now it's going to plot my x values against the residuals that those x values took on. So let's look at that. And there's our residuals. You can ignore that little corner of the line. This is what my residuals look like for this data. So this isn't bad. It's kind of random. There's no clear pattern. There's not a clear bend in it. So I kind of like those residuals. They're not looking bad. All right. What do we look for? We said we want a nice random assortment of residuals. And what does slope mean? Well, slope just tells me for every 1 unit increase in my explanatory, I experience a increase or decrease in my response. It depends on slope. And we do an example to make more sense. And the last one is, what does the y-intercept mean? The y-intercept, that just tells me if my explanatory value was 0, what would my response be at that point? It's not necessarily a terribly useful thing. The y-intercept doesn't always give us much useful information. But it just means if my x was 0, what would my response variable, what would its value be? So this is what we did. We had a chance to do a little exercise in class. You got to do some of it at home, where we had to find students take a high-stakes math test in order to graduate. With such pressure, many students become nervous, which may interfere with their ability to perform well. Researcher gets 24 student volunteers for a test. Psychologist interviews them before the math test, assessing their anxiety on a scale of 1 to 10. Then I have them take the math test. We will see is there some kind of association. Is there a correlation between the anxiety before they took the test and the math test score they achieved? Which kind of tells me my anxiety level must be my explanatory variable since it's happening first. And that means my math test must be my response. Right. So let's see how I could use this information. Okay, from the scatter plot, does there appear to be association? So I load this data in my calculator. This is my scatter plot. It's a little tough to see, but I kind of see, to my eye, there looks to be a general trend downwards. That's what it looks like to me. Okay, I'd say it looks to be a negative. Let's clean that up. Oh, moderate strength association between, we said, anxiety and test score. I don't see a really strong association, but it looks like there's some association there. I'll take my lines off there. We don't need them. Okay. Next one is find the correlation. We said we're going to use that stat calc linear regression to find it. Running at this, I found my R value is 0.525. I'm sorry, negative 0.525. And that does indicate there is a negative, moderately strong. It's not a very strong association. A strong association should be like a negative 0.8. That would be a strong association. So this is a moderate strength. Try that again. Let's get that eraser back. Oh. But there's a negative, moderate association. So it's confirming what we've already written. I interpret our R squared. R squared is right here. 0.2756 or 27.6%. Now, a standard statement we use for this is that 27.6% of the variability in test scores is accounted for by the linear model, and I should have said of anxiety level, or of the anxiety scores. I want to create the linear model. Well, that's not too bad. I'm going to use what I have right here. It tells me y equals a plus bx. Set my explanatory, so my math score, and it's a prediction, so my predicted math score equals a plus bx, or 91.66 plus bx. That's a negative, so I can just go and put that in, 4.486. And that was times anxiety. And that's my linear model. It's my model of anxiety scores to get predicted math scores. Next thing, is the linear model appropriate? I create and discuss residuals. Well, these are my residuals. In fact, we saw those before. Looking at my residuals then, it looks like my linear model is appropriate. In fact, if I look at these, I'm going to draw on these. It looks fairly random. I don't see a clear pattern. There's no clear bend. They're not fanning out or closing in. They're not doing this. They're also not closing in. They appear to be kind of generally keeping the same distance away from the zero. So it appears that there's a certain amount of stability in those, and that's what we wanted. So interpret the slope of the line. The slope line was a negative 4.48. I'd probably round that down. And what I would say is that for every point increase in anxiety, a student's predicted score is going to decrease by 4.5 points, and that's exactly what we see. I interpret the y-intercept. If a student had zero anxiety, which is my x values, they'd have a predictive score of 91.7. Now, if we think about that, that may be true, it may not be true. Our model only accounts for 27% of variability. So whether or not there's any truth to that, I don't know. Last one, it's kind of hard to read perhaps. Does this prove that anxiety interferes with student performance? Okay. And no, it doesn't prove that anxiety interferes with student performance. In order to prove that anxiety interferes with student performance, I'd have to do an experiment. This is an observational study. I'm not manipulating any of their anxiety levels, so I cannot prove causation. Okay. So let's see, though, what's going on here. We're assuming that this is true, but we don't know it's actually true yet. That's where our test is going to come in. It's going to help us determine, is this reliable information? Because I can use randomly generated figures and also get some weak associations. But if it's random, they're associations by chance. The real R would be 0. So I did some before, and I got an R of 0.383. This is purely randomly generated. I've got another one I did. I managed to get 0.31. I did a couple more. And I finally managed to get one that was above 0.4. It's not much above 0.4, but it's a little bit above 0.4. So we can get fairly weak associations purely by chance using random noise and say there's some association there. Now, it took me many times to make this happen, but we don't know that our sample has an actual association yet. So let's try and see what we're going to do with this. We're going to try and figure out this test to see, is our correlation high enough to be meaningful? Okay. Now what we're going to do is we're going to look at our test correlations and compare the slope of our regression line. Because a true correlation of 0 would mean the slope of the ideal line is 0. If it's 0, there's no association. It's not statistically significant. So we're going to use our general model of the regression line in order to do that. We haven't talked about the general model before, so we're going to do that. Every other hypothesis, we use our Greek letters for the population parameters. So our generalized model for the population is going to look like this. Our mu of y, our average y value, is equal to beta 0, which would be our y-intercept for the general population, plus beta 1, slope for the general population, times our x. And that's going to be our explanatory variable. Now, as we said, beta 0 is our y-intercept, beta 1 is the slope, and we're going to estimate it using information from our sample. We have our sample information, so let's go ahead and try this. We're going to try to create a 95% confidence interval for the slope of the anxiety and math test data. In order to do that, first we have to plan what we're going to do. Okay. Now we wonder whether the weak relationship we saw is only 0.5. Is that between anxiety and math score, is it evidence of an actual relationship, or does it just look like it and it's just from sampling error, just some random noise fell in there? So make our hypotheses. Null hypothesis, there's nothing happening. That means my null is that there's no association between math test score and anxiety level. Now my symbols for that would be beta 1, my slope would be 0. There's no association. Because if my R is actually 0, then my slope is going to be 0. Now there could be a linear relationship between math and test scores. If that's true, then beta 1 should just not be 0. This is a two-tailed test. So let's see what we can do with this. So our model. First thing is we have to run our assumption and conditions. So if you jot those down from before, first one is our data straight enough? Well, there's no obvious bend in my scatter plot. This was my anxiety levels. I don't see a clear bend in there. So it looks like it's straight enough. Secondly, are there independents? Well, there's no reason to believe one student score affects another. So, and the residuals do show random scatter. So I'm not seeing any clear patterns in the residuals. So I do look like I see this independence. Lastly, does it thicken? The residual plot shows it's kind of uniform spread. It's not getting more spread out as it goes. It's not narrowing in. There's also some limitations, and I'm just going to point this out. If we look, you might be tempted to have said that this is narrowing. Well, part of that is that we only have so much data. If we had more data, we might not see only a few points there. Instead, we could see that maybe there'd be more points like this. Maybe if we had more data, we'd have a point over here, in which case it would definitely look uniform. Only adding 1 or 2 points suddenly makes it look very uniform. The other thing is, what if we didn't have this 1 point here or here? Well, if we didn't have those, we'd be much more inclined to say it looks very uniform. So this is uniform enough. It's not going to be a perfect uniform. It's going to be fairly consistent. So last we need to know, is it nearly normal? We have to plot these residuals as in a normal probability plot. So let's go ahead and do that, and then we'll come back over this slide to show what that looks like. So I had our residuals. So let's go back to our main screen. If I want to plot those in a normal probability plot, I'm going to go to second Y, go back into our plot, and this time instead of doing the scatter plot, let's go ahead and select that normal probability plot. Now it says, where's my data? Well, my data is my residuals. So I have to hit second list and pull up the residuals. If we do that, oh, I ended up exiting out of it. Let's try that again. I went too far. There's our residuals. I've got L1 and the residuals. Try it one more time. Second stat, residuals. There they are. And let's see what we got. So I plot my residuals this way. And that vertical line is not very important in this one. It's being used for something else. But I can see, in fact, we can get rid of that if we want to. There's our residuals. Okay. They actually look pretty straight to me. And what we've done before is whenever we've had a normal probability plot, that's what we wanted. We want them to look fairly straight. So I'll bring all that back. Residuals look nice and straight. Now, as I'm answering these questions on FRQ, I need to sketch all of these plots into my answer because this is how I show I've done each one of these. So as a refresher, when we're doing these, the normal probability plot, I don't need to annotate any scales as far as what the data is. But I just want to emphasize this. Let's use the highlighter for this. I need to make sure I'm including information so people can tell what my plot is actually showing. I need to tell them what they are. It's the residuals from the predicted values. It's anxiety level to the math test score. You need to plot these. Normal scores versus residuals. Okay, we have to annotate what we're doing. Now, the nice thing is for the normal plot, the x-axis is always normal scores. And for this, it's just going to be residuals. But make sure you annotate these other things. We have to annotate our graphs. And this is a refresher of what we did back in chapter 7 and 8. So I'm not going really in depth into that. Okay. Lastly, since we're dealing with samples and means, we still use a student's T model. That hasn't changed. But we need degrees of freedom. In this case, it's n minus 2. Our sample size minus 2. Because we have 2 unknown parameters. It's saying that anxiety and the mean test score. I have 2 variables. So I need to use both of these. But I get to use the Lin-Reg t-test. We don't even mess around with this. We go straight to the calculator. Stat, test, Lin-Reg t-test. But make sure we store the regression equation. That's why I had to do that before. If I do that, we'll pull that up. Okay, so let's see what we get if I do that. Stat, and I erased the equation before, so I'm going to resave it. Let's get out of there. Stat calc, 8. And we're going to save our linear regression line into y1. Then we tell calculate it. That way it's saved it. So stat test. And we do Lin-Reg t-test. That's what we said we're going to be using for this. And it asks me where my x is, where's my L2s. And down here it's getting to what do I want to test? And where's my linear regression line? So it's asking me what all this information is. So we'll put some of this in here now. We're going to come back to this. And it says, what do I want to test? That beta and p, are they equal, not equal 0? Are they less than 0? Are they greater than 0? So let's go back over and try and finish up what is it we're testing. Because as I recall, we didn't actually run our hypothesis or anything yet. So let's go ahead and finish up our mechanics. Okay. So we've used our calculator before when we did this. But if I just gave us a computer output, we just want a quick refresher. How could we have found some of that stuff? Like our R. Oh, it's right here. Our dependent variable. Our response variable. That's what's called dependent. That's math test. So if all you use computer output, we have to know how to do this. Well then, I see that. That's my response. That's dependent. I look around a little bit more and I see my variables down there at the bottom are named constant and anxiety. Well, constant is just my y-intercept. Anxiety must be what is going to have the coefficient in front of that. Anxiety must be my explanatory. But my predicted is math. So I get math hat. Constant, like I say, gives us our y-intercept. Our anxiety level, that's the coefficient for times anxiety. So I put it on there. I've got my linear model. I have my r squared value, 27.6%, which means when I need to find r, I take the square root of that, and I use my b to make sure I put a negative on there. And that's how I get my r value. Now in this, we're now getting ready to run this. Our p-value is given to us here. In fact, if we look, we can see it. But we can find it another way by using our confidence interval. Okay. First of all, our p-value is very small. Let's circle it. If we look, they give it to us right here. Let's make sure. Okay. So probability, let me get this. We have a very small p-value. Okay, so we would reject the null hypothesis. There is strong evidence that on average, lower anxiety scores are associated with higher math scores. Now, confidence interval. We're going to use calculator for it. But this is how we do it manually. B1 plus or minus our critical value, depending on our level of confidence, for 22 degrees of freedom times the standard error of B1. If we look, B1 is our slope. And we have it here. What's our standard error? 1.551. Now in our calculator, we're going to do ln-reg t interval. So let's go ahead and let's go back to our calculator. Let's try this, because now we want to make sure of what we had for our values. So ln-reg t test, our hypothesis is that it's either linear, in which case it's not equal to 0, or it is 0. Our null hypothesis is 0. So we want to make this not equal to 0. Okay. Now let's go ahead and run our test, see what it says. So it gives us our p-value, 0.0084. Our p-value is less than any level of significance we're likely to use. So it's already told us what we found before. It was already given to us on the other one, but I want us to actually run the t-test. We can also use the calculator to do our t-interval. And as we said, it's stat, test, ln-reg t-interval. If we go in here, it asks us where's our x data, where's our explanatory, our response, frequency leave alone, confidence level we have to decide, and where is the linear regression line. So we have to remember where that's at. Now let's go back over. See what we're working with. As we said, our p-value was given to us 0.0084, but they're probably not going to give it to you if you have to solve this. We're going to make a 95% confidence interval. Oh, I'm sorry, it did say 95% at the top. So let's run our 95% then. We're going to calculate it. So I am 95% confident that my slope is between negative 7.7 and negative 1.2, which is an odd way to say that. I'm probably going to turn these around to a positive values at some point. So I have that on the other screen. Let's see how we would have phrased that. And that what I'm saying is that for every point that anxiety increases, my test score is decreasing between 7.7 and 1.3 points. And I know that's a 95% confidence. So now I go back over, and that's my first draft of saying it. To run this through, we have our interval. That contains the average math score associated with it. In other words, every unit of anxiety level is associated with an average decrease of between 1.27 and 7.70 points on the math test. And that's it. That's my confidence. Now, the other thing, this would have told me right now, I could reject the null hypothesis. Because these slopes, 0 is not in my interval. Just like we've done before. When it wasn't inside of our interval, we were able to reject that null hypothesis. This one, we'd be able to do that again. Just using our confidence interval, we could reject our null. So the next one we have, a little example here. Calculating 95% confidence interval for the cost per mile given the following information for flight information out of Atlanta. So we have Atlanta to Baltimore, Boston, Dallas, Denver, Detroit, Kansas City, Las Vegas, Miami, Memphis, Minneapolis, all these cities you can go to. We have how far it is, we have how much a fare is, and we have some summary statistics. But even better, we already have the computer output. So our dependent variable is fare. R squared is 48.2%. I have my coefficients for variables for constant. So let's do this. No, give me the highlighter. We have these. We have our coefficients. We have our standard error. We have our R squared values. We know our response variable is fare. We know distance was our explanatory variable. And we already have a p-value, 0.0014. That's a very low p-value. I can reject the idea that there is no actual connection between them because of that p-value. But in order to find my interval, it's beta 1 plus or minus t degrees of freedom times the standard error of B1. So if I look at this, it shows me how many sites we went through. We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. If I had 18, then I have 16 degrees of freedom. And yes, that's here also, but if you didn't have everything, we still have that. So I have 16 degrees of freedom. So I'm going to need that t-score for 16 degrees of freedom in order to build a 95% confidence interval. And we can look some of these up, by the way. I'm sorry. B1, 0.0786 plus minus t for 16 degrees of freedom to 95% confidence times our standard error of B1, 0.0204. If you've forgotten how to do this, you take that 94% confidence, that means you have 5% left, cut it in half, 2.5%, you're going to load that into inverse t with 16 degrees of freedom, and you're going to get that 2.12. We'll actually take this, do the math, and work it out. Oh, let's pull that back up. So we can see our interval, 0.035 to 0.122. And what does that mean? Well, remember, our explanatory is distance. So for every unit that distance increases, our slope is causing a change of positive 0.035 to 0.12. Now, that's kind of an odd way to say it. We like using whole numbers. So in order to make these into whole numbers, I'd multiply them by 100. I would get 3.5 to 12.2. But that means I had to multiply my distance by 100. So for every 100 miles someone flies, their airfare, it appears, will go up by somewhere between $3.50 to $12.20. That's based on 95% confidence. So I've already said it. I'm pretty sure I have this on next screen also. But that's it. We're 95% confident that that interval contains the average fare difference that's based on this. So in other words, every 100 miles traveled has an associated cost going up of $3.50 to $12.20. Okay. Again, these are going to take a little bit of practice to get out. There's a lot more context in these. Okay. Should be long enough to have read the screen. If you need to, you can pause it and come back. Exactly how we found it. We got our interval. So let's have it up here twice. Okay, so this is where we're at. We have some homework questions. We'll try these out. This is the last chapter we have of the textbook before we start going into just review and getting ready for the final, getting ready for our test. So, page 658, questions 2, 3, 6, 7, 18, 20, and 25. And some of these are going to be a little tougher. Might want to work with a buddy on some of these. But the idea is work them out, get to the answer. I'll still give you the solution guide to these. Because in that way, if you still have a question, though, you need to say something about that, not wait. Don't just accept the solution guide and say you got it. If you're not sure why the solution guide, why we take the step that we do, you need to say something so we make sure we get that answered. All right, I look forward to seeing you in class.